Dear students, today we will start a new chapter in which we will try to learn the complex variable technique to solve the flow problems. So before starting complex variable technique, we will revise a concept of stream function and potential function, which I have already told you. Stream function and potential function. If you remember, for a two-dimensional flow, if I write the streamline, equation of streamline, then it is in Cartesian coordinate, it is dx upon u dy upon v, which you can write as v dx minus u dy is equal to 0. Let us assume that this equation 1 is exact differential equation. So this implies there exists a function, say psi. This is a scalar function of x and y, because this equation is in Cartesian coordinates x and y. So this function has to be a function of x and y such that v dx minus u dy is equal to d psi, because you have said that let it be exact. It is equal to 0, so you have to write it equal to 0. Now v dx plus minus u dy is equal to d psi may be written as delta psi delta x dx plus delta psi delta y dy. This implies v is equal to delta psi delta x and u is equal to minus delta psi delta y. So you can say that these are the relations between velocity components and this psi function. This psi function is known as stream function. And these are the relations of u and v in terms of the stream function. Further, you see that t psi is equal to 0 implies psi is equal to constant. So along a streamline, or you can say along a line, psi is constant and the line is called the streamline. And because you have used the equation of a streamline, you have introduced a function. This function is called the stream function, and d psi, giving psi to be constant, is called a psi is constant along a streamline. In another way you can also prove it. Suppose for an incompressible flow, one more important thing is that when you write the streamline equation, this streamline equation is necessarily for incompressible flow. This is important point. Now in another way you can say that if you have an incompressible flow, then for this incompressible flow, equation of continuity is delta u delta x delta v delta y is equal to 0. And for this equation, you may write delta delta x, in place of u, you will write minus delta psi delta y plus delta delta y delta psi delta x. This is left hand side. and solving it you get 0. So this implies equation of continuity is satisfied. Which is the necessary condition for a flow to be possible. Now conversely we may say that if psi is constant along a line, then that line will be a streamline. If psi is constant along a line, the line will be a streamline. As I have already introduced psi, that is psi is equal to minus delta psi delta y is equal to u, and delta psi delta x is equal to v. So we will use this relation. First of all, we say that psi is constant along a line. We have to prove that the line is a streamline. This implies d psi is 0 along a line. This implies delta psi delta x dx plus delta psi delta y dy is 0 along the line. Further, this implies that v dx minus u dy is 0 along the line from B. Implies dx upon u is equal to dy upon v along the line. Now this is the equation of a streamline. So this implies equation is a streamline. So we have proved that if we have a streamline, we may define a function psi, which is a stream function which is constant along the line. And conversely, we have proved if psi exists with the relations with u and v, and if psi is constant along a line, then that line will be a streamline. Other conditions on or other characteristics of the stream function I have told you earlier. The one more thing is that this stream function is also known as current function. Current function is another name of stream function. Now, physical significance of streamline has been taught to you earlier. And again, the velocity components in terms of psi I taught you earlier, which I am writing again, that if I am having the radial component of velocity, this will be minus 1 upon r delta psi delta theta, and if I am talking about transverse component of velocity, this will be delta psi delta r. These are the velocity components in terms of psi and in terms of stream function psi. These are the radial components of and transverse components of velocity in polar coordinates. Now there is another function which is a potential function. These are the two functions which will be required to define complex potential technique. So next one is complex function, potential function. This is written as phi. First thing is that stream function and potential function describes the line such that the lines are perpendicular to each other. So streamlines and potential lines are perpendicular to each other. This is a very simple proof, and you can see this in any book or on internet or in every book you may find this relation, that how the streamlines and potential lines are perpendicular to each other. Now we would introduce the potential function. First of all, we will introduce the potential function, and to introduce the potential function we will use the theory of irrotational flows. Suppose there exists a scalar function phi. Again, this is a function of x and y such that q is described as delta phi. Many times we write q is equal to minus delta phi. Phi is a potential function, and when we write q is equal to delta phi, that simply means we are talking about the flows in which we are describing our flow from low potential to high potential. And if I am writing the minus symbol, then it simply means that we are going from high potential to low potential. Now applying the curl on the both sides, curl of q is equal to curl of delta phi. Because phi is a scalar function, it is a scalar function, so it will be gradient, and curl of gradient is 0, so it will be 0. This implies, and you know that what does this condition imply? This implies that your flow is irrotational. So this implies existence of potential function establishes the flow to be irrotational. That flow is irrotational. Conversely, if flow is irrotational, velocity may be described in terms of gradient of a scalar function called velocity potential function. So now we will see that how can we introduce this type of function. Suppose the flow is irrotational. Let the flow be irrotational. So what is the condition for a flow to be rotational? Delta cross q is equal to 0 everywhere in the flow domain. Now consider a simply connected flow region. Simply connected flow region such that a closed curve C is fully immersed in it. Like this is the flow region, and in this flow region you consider a closed curve C. This is a closed curve C. You may write this part from O to P as C1 in this direction, and O to P in this direction as C2. S is the simply connected region. Now what does Stokes theorem says? Integral around the curve C q dot dr. What is this? This is the circulation. This may be written as surface in which this C lies, curl of q ds. Curl of q is a vector. Either I write dot nds or I write dot ds. Now if I write dot ds, then this ds is a vector. Now because delta cross q is 0, this implies integral C q dr is equal to 0. Now I may write this C as OP plus PQ, because this C consists of one portion OP and then PO. This is PO. PO q dr is equal to 0 implies OP q dr plus PO q dr is equal to 0, or OP may be written as C1. So this is C1 q dr. Sorry, when I am writing OP, I have not to put this closed curve. OP and PO dr. C1 q dr plus, now this PO and this is C2, so writing minus C2 q dr is equal to 0. C1 q dot dr is equal to C2 q dot dr. This simply means that this flow along C and this flow along C2 both have the same value. That is, when you move from O to P, either through C1 or through C2, this is having the same value. It implies that q dr does not depend on path but depends on endpoints. So if I say that there exists a solution of it, I write q dot dr is equal to d phi, and this d phi is depending upon the endpoints O and P. Or I may write it as OP delta phi dot dr, and then comparing, I write q is equal to delta phi. So what is this phi? This phi is called velocity potential function. Many times we write q is equal to minus delta phi. As I told you earlier, if you go from high potential to low potential, or q is equal to delta phi when you go from low to high. So potential flows are characterized by irrotational velocity field. Irrotational velocity field. Now equipotential lines are the lines along which phi is equal to constant. Similarly, I can say that equistream lines are the lines along which psi is equal to constant, because these are the concepts which we will use later. And for equipotential line, you may also say that since phi is equal to constant, this implies d phi is equal to 0, delta phi delta x dx plus delta phi delta y dy is equal to 0. And value of delta phi u dx plus v dy 0 implies dy dx is equal to minus u upon v. This is called slope of potential line. So in this way we have introduced the potential function. Now suppose you have noticed one thing, that when we introduce the stream function, we take an assumption that the fluid was incompressible. But when we consider or when we introduce the potential function, it is introduced only for irrotational flow. So psi function, that is the stream function, is associated with incompressibility. This is very important point. And phi function is associated with irrotational flow. Okay. Now I take one condition. Suppose I say that fluid is incompressible also, because incompressibility is not the necessary condition for the introduction of potential function. What is the necessary condition? That the flow should be irrotational. And what is the necessary condition for psi to exist? Is that the fluid should be incompressible. Now suppose fluid is incompressible also, incompressible as well as irrotational. Then we know that equation of continuity for incompressible flow is delta u delta x plus delta v delta y is equal to 0. Now put u and v in terms of phi. We get delta 2 phi delta x2 delta x2 plus delta 2 phi delta y2 is 0. This implies phi is harmonic function. It simply means that phi to be the harmonic function is not necessary. Phi will be the harmonic function only when your fluid is incompressible as well. So it implies that potential flow may exist for compressible flow as well. These exist for potential flow exists for compressible as well as for incompressible flows. Similarly, if the flows have strong vorticities, flows with strong vorticities may not be approximated by potential flows. Why? Because irrotationality is the necessary condition for a flow to be potential flow, approximated by potential flow. So flow with strong vorticities may not be approximated by potential flows because the necessary condition for potential flow to exist is that it should be irrotational, and if it is irrotational then there will be no vorticities. Now equipotential lines, along the equipotential lines we know that the potential function, that means phi, is constant. Now it has applications in air, in groundwater flow, in acoustics, in water waves, electrosonic flow, motion of streamlines, wears, and there are so many applications of potential flows. The reason being that in these type of flow regions, the fluid accelerate rapidly from the state of rest. So there are no chances of rotation. There is no history of rotation in such type of flows, and therefore these type of flows may be approximated by the potential flows. Now we come to complex potential function, which is a function which will be introduced every time when we want to use the complex variable technique. So it is a part of complex variable technique. Initially you have read the velocity potential function, and it is the complex potential function. So do not be confused between the two. Velocity potential function exists for the for those type of flows where the flow is irrotational. And when I come to complex potential technique, complex variable technique, I will need both the functions, the stream function as well as the potential function. And we know that if I need psi, that means the stream function, my flow should be incompressible. And when I need phi, my flow should be irrotational, right? And if I need both, then my fluid should be incompressible and flow should be irrotational. So under the existence of both the conditions, I say that U was defined as delta phi delta x, V as delta phi delta y. And similarly, in terms of psi, U was defined as delta psi delta y, and V was delta psi delta x. Combining the two, I may write that delta psi delta y is equal to minus delta phi delta x, and delta psi delta x is equal to delta phi delta y. If you can recognize these equations, these are Cauchy-Riemann equations. Further, as we know that U and V are continuous, and these are written in terms of U and V, this implies delta phi delta x, delta phi delta y, delta psi delta x, and delta psi delta y. All the four components are also continuous. So if these are continuous and Cauchy-Riemann equations are satisfied, this simply means that there exists an analytic function, which you have read in complex analysis, analytic function. Say I denoted this function by W, such that W is equal to phi plus I psi. Naturally, if I am defining a function which is complex, so I am working in a complex plane, this W is in fact a function of Z, where what is this Z? Z is equal to phi plus I psi. If I write delta W delta Z, then this will be Rather I write delta W delta Z will be dW dz delta Z. No, I'll tell you this later. dW dz delta phi delta x dx dz plus, oh sorry, here W is a function of Z, where Z is defined in the complex plane x plus iy. Now since W is analytic function of Z, you know that if a function is analytic function in a complex plane, there may exist a conformal mapping. There exists a conformal mapping from Z plane to W plane, provided, what is the condition? That dW dz is not equal to 0. Further, if dW dz is 0, it means that there exists a stagnation point. The reason being that you can easily see that dW dz will be u minus iv. U plus iv or minus u plus iv as you define your phi. And u is a velocity component, v is a velocity component. If I write dW dz is equal to 0, it simply means that u and v both are 0. So it is called the stagnation point. So this is the introduction of complex potential function. Now how will we use this complex potential? I'll teach you in the next lecture. Thank you.